Sometimes, finding faults becomes very difficult, and they are such that you don't understand what the problem is. In today's video, I have these two PCBs in front of me. Look, this one is for the indoor unit, and this one is for the outdoor unit, and it's showing an F6 error. But how is the F6 error occurring? That's what I'll explain to you. I found this fault with great difficulty, but I finally figured it out. However, I will explain it to you step by step, because if I tell you directly, you won't understand how to actually find it. I have now turned on the electricity, and look, the display turned on once and then turned off. And now, look, it has turned back on, and it has also started the indoor fan motor. Whenever you encounter such a fault, you must physically inspect which components are causing the problem. This will make it easier to detect the fault. Now, the fan motor started once and then stopped. Now it has started again. Normally, the unit is installed above, and we don't understand why the F6 error is appearing. Sometimes we assume that the outdoor PCB is faulty or the wiring is damaged. Now look, as soon as the fan motor stopped, it started showing the F6 error. What's happening here is that the switching relay is not turning on under any circumstances. Someone has already worked on this PCB before, but the issue was not fixed. Now, since the relay is not turning on, it is not supplying power to the outdoor unit. And when the outdoor unit doesn't receive power, the F6 error is bound to appear. Before working further on the indoor PCB, I will first show you how the outdoor PCB is functioning. Now I will turn it on, and as soon as I supply power directly to it, LED 2 turns on, and it has also switched, which means that the PCB is in a working state to some extent. This confirms that the issue lies in the indoor switching relay, which is not functioning, and since the indoor relay is not working, it is not supplying power to the outdoor unit. As a result, the F6 error is inevitable. F6 is a serial communication error where both the indoor and outdoor units shut down and no functions operate. Sometimes the indoor blower motor might still be running, but the system continues to show the F6 error. There can be 4 to 5 possible reasons why this switching relay is not turning on. Although this issue is rare, since we have encountered it, we have no choice but to troubleshoot it. This is a 12-volt operated relay, and the SMPS system in the PCB generates 12 volts to power this relay. The microcontroller then controls it via a Darlington array, specifically the ULN 2003 Darlington array in this case. This array is responsible for switching the relay on. You can see this mark here. It's the mark of the coil. Positive voltage comes from this side, and negative supply comes from this side, so the relay turns on. When it's off, the point here is disconnected, and when the relay turns on, the mark here connects to this point. This connection links to the communication and voltage detection circuits, completing the entire function. If the relay doesn't turn on, its communication and voltage detection circuits won't work, and it will display an F6 error. Now, that was a simple explanation of how the relay functions. Let's move on to diagnosing the actual problem. Why isn't the relay turning on? There are different methods to troubleshoot this issue, as a single method won't always work. The starting point depends on the situation. Since I have the physical PCB in front of me, I tested it from multiple angles to find the fault. For someone who isn't highly trained, the first step would be to check the 12-volt supply, because if the 12-volt isn't present in the PCB, the relay won't work at all. If the 12-volt supply is available, then there's a 100% chance that the relay should function unless there's another issue. However, sometimes the microcontroller has a fault that prevents the relay from operating even when the 12-volt is present. Now, let's check where the 12 volts is being generated in the circuit. Here, we have the SMPS section, and this is its MOSFET and chopper transformer. We have the step-down transformer, and this is the EC3 capacitor, where the 12-volt supply is typically generated. Let's check here to see whether we're getting 12 volts or not. We power up the PCB and measure the 12-volt output by placing the positive probe on the positive terminal and the negative probe on the negative terminal. We are getting a stable 12.9 volts. The SMPS is working correctly and supplying the required 12 volts. Now next, we will check whether this relay is receiving 12 volts or not. The positive supply should be present on one side of the relay coil, and this other pin is the negative voltage pin. No voltage is reaching the relay. The relay is not receiving 12 volts, which is why it is not turning on. The microcontroller might not be sending the signal to turn on the relay. Then, this could also be possible. The Darlington array, ULN 2003, which receives signals from the microcontroller, might not be working properly. The Darlington array itself could be faulty, preventing the relay from switching on. Now, we need to trace the exact issue by checking these components step by step. Now, We need to check whether the microcontroller is sending its signal and whether the Darlington array is generating it properly. There are different methods to check this, and I will explain it to you step by step so you can properly test the microcontroller signal. The Darlington array, ULN 2003, controls the negative voltage to switch the relay. The negative supply comes in and passes through a jumper before reaching pin 14 of the Darlington array. This means that pin 14 is receiving the necessary supply. Now, for the relay to activate, the microcontroller must send a signal to pin 3 of the Darlington array. I'm checking it right now. Let me show you where it's connected. Set the multimeter to continuity mode. Check the path between pin 3 of the Darlington array and pin 3 of the microcontroller. If the multimeter beeps, shows continuity, this confirms that the signal path is connected. Now that we've confirmed the connection, the next step is to check whether the microcontroller is actually sending a signal. When the microcontroller sends a signal to pin 3 of the Darlington array, ULN 2003, the 14th pin of the Darlington array connects directly to ground. This allows the ground path to complete, which activates the relay and makes the entire system function properly. Important point to remember, the positive voltage for the relay is always directly supplied. You must also check whether the positive voltage is reaching the relay. Let's understand this in a simple way, because if I explain it to you using an oscilloscope, this video will become quite long. And as I've already explained, how the microcontroller's voltages work with the Darlington array. As I mentioned earlier, the presence of both positive and negative voltages is crucial for the relay to turn on. If either one is missing, the relay will not activate. Now, let's check if the Darlington array is switching the negative supply properly. As I previously showed, this jumper is connected to the Darlington array. To test this, I will place the negative probe of the multimeter on this point, because if the Darlington array is functioning correctly, it should switch the negative point, ground, and we should detect a ground connection here. However, when I measured, there was no voltage present at this point. To confirm if the ground is actually available, I will keep this probe at the same point and check against a known 12-volt source from the capacitor. If ground is properly present, we should see the full voltage difference, close to 12 volts. When measured, the reading shows 11.45 volts, which confirms that the ground is present and the Darlington array is switching the negative supply. However, I have not yet checked the positive supply, so it is possible that the issue lies there. Alright, let me tell you what the fault is with it. Now, it is confirmed that both the microcontroller and the Darlington array are working correctly, and the negative supply is reaching the relay. The next step is to check whether the positive supply is also reaching the relay. The positive voltage from the SMPS is working perfectly, but we need to verify if it is actually making it to the relay. The positive supply travels along the PCB traces, with both positive and negative lines running together. The black line underneath indicates how the voltage is routed. The positive supply should reach this specific point, where a 0-ohm resistor acting as a jumper and a capacitor are present. From here, the voltage passes through a jumper, which carries it further along the circuit. However, at the relay connection point, the positive supply is missing, which is why the relay is not turning on. The possible cause could be a faulty 0-ohm resistor, preventing the voltage from passing through. To confirm, I checked the resistor, and it is working fine since it is being used as a jumper. This means the issue lies somewhere else, and the next step is to trace where exactly the positive voltage is being blocked or lost in the circuit. I checked the continuity along the trace, and it is completely fine. However, when I measured resistance from the resistor to the next point on the trace, I got a reading of 25.6 megaohms. Since this is just a wire trace, the resistance should be 0 ohms. If the resistance is too high, the voltage cannot pass through properly, which means this trace is causing the issue. Let's clean its print a little bit. After cleaning, I verified that the trace was indeed leading to the correct point. Now, I will attach this wire to the capacitor's positive pin and connected it properly with RJ21. I set the multimeter to ohms mode and measured the resistance again. Now, the resistance value dropped to 0 ohms, showing 0.3 ohms, which is normal. This means that the voltage can now pass through properly. I turned the PCB on, and immediately, the relay activated. Measuring the voltage at the relay, I found 11.27 volts present. This confirms that the issue was caused by a faulty PCB trace. Normally, PCB traces, prints, do not get disturbed, and such issues are very rare. However, in this case, the trace had developed high resistance, which caused the problem. Now that the relay is working, I need to connect the indoor and outdoor units to check if they are communicating properly. Now, on top of it, we will apply the UV mask. The indoor unit has successfully completed switching, but now we need to confirm whether it is properly communicating with the outdoor unit. The multimeter is set to DC voltage mode. Let's connect the probes to the communication and the neutral wire to check the signals. The outdoor unit has started working, and its LED indicators are blinking in a normal pattern. There are fluctuations in the voltage readings, which is a sign that communication is happening. In such cases, when the voltage fluctuates, it generally means the communication is okay. Even though the communication seems fine, it is important to check for any errors after connecting both units. Sometimes, a unit may still show an error despite communication being active. However, in this case, everything looks fine because the F6 error has not appeared and the motor is running smoothly. Click on the left or right thumbnail to watch our next videos and subscribe. Thank you.